Hi, today we are going to discuss Chapter 7 of Ionic Equilibrium. In this video, we are going to discuss Part 3 of Acid and Bases for Buffer Solutions. Here are the learning outcomes for these lessons. At the end of these lessons, students should be able to define buffer solutions, describe the qualitative how a buffer solution controls its pH, derive the Henderson-Hasselbalch equations, and calculate the pH of a buffer solutions. What is the buffer solution? A buffer solution is a solution which has the ability to maintain its pH even though a small amount of a strong acid or a strong base is added to the solutions. A buffer solution is a solution that contains a weak acid and its conjugate base, or a weak base with its conjugate acid. A buffer solution is able to neutralize either a strong acid or a strong base that is added. The strong acid added is neutralized by the base of the buffer solution, while the strong base added is neutralized by the acid of the buffer solutions. There are two types of buffer solutions. An acidic buffer solutions, which has pH less than 7, and a basic buffer solution, which has a pH more than 7. First, let's discuss an acidic buffer solutions. An acidic buffer solution is prepared by mixing a weak acid and its conjugate base. For example, a mixture of ethanoic acid and sodium ethanoate. The reaction that occurs in the acidic buffer solutions, as shown in the equations. There are two types of reaction that occurs in the reaction. First, the dissociation of the weak acid and the dissociation of the salt. The dissociation of the weak acid in this reaction are partially dissociated in aqueous solutions. For salt, the dissociation involves a completely dissociated in the aqueous solution. In the mixture, the ethanoic acid acts as a dominant acid in the buffer solutions, which has the presence of H+ ion, which is a very small amount due to the partially dissociated of the ethanoic acid. For the ethanoate ion, it acts as a dominant base in a buffer solution, which is mainly come from the complete dissociation of the sodium ethanoate. When a small amount of strong acid is added, most of the H+ ions will be consumed by the ethanoate ion, which is a conjugate base to form ethanoic acid. The chemical reaction involved as shown in the equations, which is the ethanoate ion is react with H+ ion added from the strong acid to form the ethanoic acid. The equilibrium will shift to the left, thus the concentration of the ethanoate ion will decrease while the concentration of the ethanoic acid will increase. As a result, there will be only a small change in the pH. But when a small amount of strong base is added to the solutions, the OH- added will be consumed by the ethanoic acid to form water. The chemical reaction as shown in the equation, whereas the ethanoic acid is reacted with OH- ion from the strong base to form ethanoate ions and water. The equilibrium of this reaction will shift to the right, thus the concentration of the ethanoate ion will increase, and the concentration of the ethanoic acid will decrease. As a result, there will be only a small change in pH. Besides, the H+ from the dissociation of the acid will also react with the added of OH- ions. The chemical reaction as shown in the equation, whereas the H+ ion is reacted with the OH- ion from the strong base added to form water. The equilibrium position of this reaction will shift to the right to increase the amount of the H+ that consumed in the reaction. Thus, the ethanoate ions will increase in concentration and the ethanoic acid will decrease in the concentration. As a result, there will be only a small change in the pH. Now, let's discuss on how to calculate the pH for the acidic buffer solution. Let's use the same example of acidic buffer solutions that contains a mixture of ethanoic acid and sodium ethanoate. The dissociation constant Ka can be expressed as Ka equals to concentration of the ethanoate ions times concentration of H3O plus ions and divided by a weak acid of ethanoic acid. Ka expression can be rearranged in terms of concentration of the H3O plus ions. When place the negative log on both sides of this equation, it will give a new equation, that is a pH equals to pKa plus log concentration of the ethanoate ion over its concentration of the ethanoic acid. In general, the equation shows the expression of pH equals to pKa plus log concentration of the salt over concentration of its weak acid. The above equation is called Henderson-Hasselbalch equation. Now, let's take a look for an example on how to calculate the pH of a buffer solution. The first question is, calculate the pH of the buffer solutions that contains 0.10 molar of ethanoic acid and 0.10 molar of sodium ethanoate. The Ka value is given of ethanoic acid, that is equals to 1.8 exponent -5. To determine the pH, we can use the Henderson-Hasselbalch equation. By substituting the value into the equations, it will obtain the pH equals to 4.74. Question number 2. Calculate the pH of the buffer solution after the addition of a strong acid of 0.02 molar of the hydrochloric acid. Take note that the presence of the H+ ion that is added from the strong acid will completely consumed by the conjugate base in the buffer solutions. The reaction occur in this buffer solution is shown in the ICF table. The ethanoate ion will completely consume the H+ ion that is added from the strong acid. That will give the production of ethanoic acid. Take note that the strong acid added is only a small amount. Therefore, the H+ ion in the reaction will be the limiting reactant. At the end of the reaction, we still have a remaining ethanoate ion with 0.08 molar and the ethanoic acid with 0.12 molar. For the H+, they are completely consumed in the reaction. From the ICF table, there are calculated value of the concentration of the ethanoic acid with 0.12 molar and the ethanoate ion with 0.08 molar that remains in the buffer solutions. By using Henderson-Hasselbalch equations, substitute all the value obtained from the calculation. It will give the pH equals to 4.57. Now, what happened to the buffer solution if there are a small amount of a strong base is added to the buffer solutions? We can consider question B for an example. Calculate the pH of the buffer solution after the addition of 0.02 molar of NaOH. Take note that the OH- added from the strong base will completely consumed by the weak acid in the buffer solution. Considering this reaction, the chemical reaction can be written in the ICF table. The ethanoic acid is reacted with OH- ion that is added from the strong base to produce ethanoate ion and water. Since the OH- added is only a small amount of the strong base, therefore the value will be the limiting reactant. At the end of this reaction, we'll still have a remaining of ethanoic acid with 0.08 molar and the ethanoate ion with 0.12 molar. From the calculation using ICF table, the concentration of the ethanoic acid obtained 0.08 molar and the concentration of the ethanoate ion is 0.12 molar. By using Henderson-Hasselbalch equation, substituting the value will obtain the pH equals to 4.92. In this video, we have discussed about the acidic buffer solution. Don't forget to watch the next video about the basic buffer solution. We'll see you next time. Bye!